Okay, there we go. So, last time we were talking about coordinate line integrals. This is kind of one of the last things we're going to say about line integrals for, well, at least in this section immediately. So, reminder, last time, all we did is I basically just plugged in the coordinate formula for what x prime is. That's it. And then just kind of following through and plugging it in, what we found is that we ended up with kind of an alternative notation for vector line integrals. And then we ran out of time, and I didn't have time to say much about this. So looking at this comparison between these two choices of how to write a vector line integral, which one do we like better? I proposed this one for Math 219 purposes. It's more compact, for one thing. It's also more intuitively satisfying. If you look at what's in here, F, that's going to be something physically natural. If we're talking about forces, that's the force field. If we're talking about a fluid flow, that's the velocity field. Whatever it is, that's something intrinsic and natural in the circumstance. What is dx? That's my displacement vector. This is all extremely geometrically relatable and natural, so that's the argument for that. What is P by itself? It's a coordinate of something natural, but by itself, on its own, it's not clear exactly how natural that is, without making reference again back to F, which is intrinsically natural. Likewise, what is dy by itself? Well, that suggests that as I move along the curve, that is my domain for this line integral, dy says how much did just the y-coordinate change on that little piece of curve. Well, that's weird. Right? So I think looking at what's actually on the right-hand side over here, trying to make sense out of this thing, it's just less immediately clear what these things are and why I would care about them. Right? So I think it's less clearly natural than the notation we've already got. Furthermore, notice it's quite a bit more bulky than the notation we've already got. So for Math 219 purposes, I don't think there's much argument to go out of your way to use this notation. Which brings up the question, why am I showing you this notation? Now there's two reasons. First, a cultural reason. There's this thing called differential forms. We're not going to talk about differential forms directly anyway. In this course, you can see some discussion of differential forms in Chapter 8. I will point out, Chapter 8 is quite a bit more sophisticated and mathy and proofy and abstract than Chapters 1 through 7 that we're covering in this course, which themselves are already a little mathier, proofier, abstracter than the way we're actually treating the material in Math 219. So it's a stiff drink. So be warned, right? That said, anyway, if you're curious, take a look at Chapter 8. But what I do want y'all to know is that differential forms exist and that they are ultimately natural things. It really does make sense if you take the appropriate sophisticated point of view. Again, you're not responsible for it in this course. And also, it's very important to understand they're very powerful. This is not pointless abstraction. There are certain things that you can do, important things that you can do only with differential forms. So they are a really big deal. They are important. It's just that they're important in another context that isn't us. Right? In Math 219, we're not going to use differential forms. So, like I say, cultural note. I want you to know they exist. I want you to know that they are useful. And side note, what do differential forms look like? Well, they look a lot like that. So that's a pretty strong case right there for why some people like to use that notation. And that brings me to my second point. The practical reason that I bring up this notation is that it really is in common use for good reasons. Right? Good reasons, again, that we can't really talk about here. But because they are in common use outside of this course, in the real world, as it were, you're going to see this notation. Right? Some people prefer this notation. Some people even use it by default. So when you encounter this notation, I just wanted you to be able to identify what it is and how to make sense out of it. And specifically then, when you see that notation, what I encourage you to do is to recognize that these scalar integrands are really just a fancy way of telling you what your vector field is for the vector line integral that they represent. And the dx, dy, dz business is just a fancy way of representing the position differential that's involved in the vector line integral. Again, that we would more naturally like to understand this in terms of. So that's how you make sense out of it. When you see this, think this. All right, let me pause on that. Does anybody have any questions about this here? All right. Okay, moving along. Some neat statements, neat facts about symmetry theorems. And y'all, I'm sure, recall, I'm a big fan. I love symmetry theorems. I think they're underappreciated. They're undersold in a lot of textbooks. And so, good news. We have another one for scalar line integrals. Symmetry theorem. I want you to notice, I've deliberately laid this out on the page really similarly to the way I laid out on the page the previous statements of symmetry theorems for double integrals and for triple integrals. Because this is morally equivalent. If the integrand is odd, if the domain, in this case a curve, is symmetric, then your integral is 0. Gotta love it. Right? Just be warned, you do have to be careful with this. In particular, both conditions have to hold. That's the same warning that I gave you with double and triple integral symmetry theorems. And furthermore, you have to use the same line for both of these conditions. Again, same warning that I gave you for both double and triple integrals. So, yeah, good stuff. I encourage you to use this theorem when it applies, and I encourage you again to be careful and watch out. You do have to make sure that all the conditions apply. Otherwise, the argument is not complete, and more worrisome, the theorem might not actually apply at all, and everything you've written doesn't actually make any progress. So do be careful, all the same warnings. But great theorem, I'm a big fan. Now, one other asterisk. Notice I've underlined this here. Scalar. This only works for scalar line integrals. This does not work for vector line integrals. Yet another reason that I like to make a bright distinction between scalar line integrals and vector line integrals, which, by the way, in some textbooks are kind of blurred together as being, kind of different versions of the same thing. I prefer a bright line, clear distinction between them. So again, yet another reason. Scalar line integrals only. For vector line integrals, there is no odd symmetry theorem. It just doesn't work. It just doesn't. If you want to see kind of why it doesn't work, here is a vector line integral. Vector line integral right here. And let's look at kind of the dx thing here. How does dx appear in this picture? Notice, by the way, we have a curve that is symmetric. Specifically symmetric over that line. This is a for example. So where is dx on this picture? Well, I can't really see dx itself exactly, but I can see the ds and the t, and these are easy to see here. The ds there, the ds here, looking good so far. Looking at the symmetry over this line, these two pieces do have the same size, and that's all fine. But if you look at the unit tangent vectors, you look at these t's. There's the t on one side. Here's the t on the other side. They are not the same. They're also not opposites. They're just different, right? And I wouldn't go quite so far as to say unrelated. There is a relationship, and now this is I'm going to say this just for the sake of completeness, but this is not a suggestion. There is actually a different kind of symmetry theorem that you can formulate for vector line integrals. But it's way more trouble than it's worth. It is very importantly not about odd symmetry. It is more trouble than it's worth. You can far more easily get yourself into trouble than you can get yourself out of trouble with this symmetry theorem that I'm not going to state, right? So I want to pretty much leave it as for all practical purposes, for the purposes of Math 219, we're not going to talk about any symmetry theorem for vector line integrals. Okay. How are we doing? Is everybody with me? So anyway, if you do have a scalar line integral, go ahead. If you have a vector line integral, no option for symmetry, realistically. Okay, moving it along. We're now going to go into 6.2. I want to take a quick pause here. This is a kind of a moment in the course. This is going to be our first venture into some very sophisticated ideas, some very weird seeming ideas, delicate but ultimately very powerful ideas, and I think really beautiful ideas. This is really good stuff that we're about to start getting into. There just a tremendous amount of stuff to say. You'll notice on the lecture schedule, if you look at the my target goals for where I want to be at what part of the course, the targets, what I'm planning to cover in a given day, I deliberately slowed it down near the end. And that's for a combination of reasons. Partly it's because I know I need to keep myself moving as fast as I can. Otherwise I won't be in enough of a hurry and then ultimately I won't finish. But partly also because there's so much to say about Green's theorem that we're about to talk about here. And then the related theorems such as the divergence theorem, the curl theorem, and variations of those. So, exciting stuff, beautiful results. What you're going to notice is that it's very different. A lot of really different ideas, a lot of sophisticated ideas. So, there you go. All right, so moving along. Before we can get to Green's theorem, I need to talk about certain key ideas. First thing I want to talk about is the idea of a boundary. Now, y'all know pretty much what a boundary is, right? The boundary is the kind of the dividing line between the set and not the set, right? The old concept. And so, if you have a set like this solid area here, D, part of the boundary would be this curve. Right? It's again the dividing line between set and not set. But here's the problem. We are now into the part of the course where we're going to be focusing more on vector line integrals than scalar line integrals. When you're talking about vector line integrals, as we soon will be today, a curve is not what the domain is. Right? The domain for a vector line integral is an oriented curve. That's important. It has to be oriented. I need to know which direction you're going along the curve in question. Otherwise, it's not clear which of the two options you mean, and they are not the same. They're negatives of each other. Right? So we need to talk about boundaries in this context. We need to talk about boundaries not as curves, but as oriented curves. Said differently, I need a specific convention of when I say the word boundary, which orientation should I choose? I need an orientation. Which one is it? So that's a rhetorical question. So here's the. Before I give you the answer, I want to give you just a little bit of a context. The answer is arbitrary. This is an arbitrary choice that got made a long time ago. 100, 150? Definitely more than 100. Anyway, an awfully long time ago. And so, why do we have to go with an arbitrary choice? And ultimately, we kind of don't, I suppose, except for the fact that everyone else in the world who talks about Green's theorem is all using the same convention. So my analogy for this is talking about if you've ever had a physics class and you know that protons are positively charged particles, electrons are negatively charged particles. Where did that come from? Why didn't they choose to call electrons positively charged, protons negatively charged? They could have. A strong case could be made they should have. But they didn't. The convention is what it is. Planet Earth works with this convention. Electrons are negative, protons are positive. We just have to get on board with that convention. Likewise, there's a convention here. It is arbitrary, but again, this is how planet Earth works, and we're going to have to stick with that. So here's the rule. Arbitrary, but standard. And that is, when you're moving along the boundary, here's our boundary curve. Again, the direction we move is the direction such that as you move that way, you need the domain to be on your left. Right, so imagine that this purple boundary curve is a path on the side of a lake, nice little scenic lake, and you're having a pleasant afternoon walk, and you're walking along this trail. Make sure to walk whichever direction puts the lake on your left. Again, arbitrary, again, standard. So, which direction of the two that I could go here puts the lake on my left? And, for this curve here, that is the direction, that is the orientation that puts the lake on my left. Puts the region D on the left. Okay. Now, what about this other scenario? Here's a piece of curve that's part of the boundary of this gray region D. Which direction do I have to go in order to put the lake on the left? To put the region D on the left? Well, again, two different ways that you could walk, and you have to imagine yourself actually kind of walking along one way or the other. Think it through, and, this way. If you're walking that way along the curve, the region is on your left. Is everybody on board? Any questions? Feel free. Okay. Totally arbitrary, completely standard. Okay. Now, there is a sloppy version of this that has its purposes, I suppose. But do be aware that this is sloppy and not reliable, and you shouldn't trust it. But some people point out that, if this is your region and the boundary curve is like this, and which direction do you go to put the lake, put the region on your left? Well, I'd have to go that way. That puts the green region on my left, and check it out. It's always counterclockwise. So some people will present it as counterclockwise. And I just have to point out that it's not the same, and it's also not good enough. Problems will arise. If you insist that your convention is that the boundary is oriented counterclockwise, you will not be able to develop Green's theorem. It will not work. It just crashes and burns. It doesn't work. So this is not an acceptable convention, that boundaries are counterclockwise. Counterexample. Let's consider this region here. Right, there is a two-dimensional region, and we can talk about its boundary curve, and notice that if you go that direction along the boundary, region's on your left, you're going counterclockwise, looking good so far, everything seems fine, but on this curve, again, that is part of the boundary. Right, that's part of the boundary of the lake. There's a couple of islands in the middle of this lake, right? But nevertheless, this is part of the shoreline of the lake. And if you go such that the region is on your left, as I've drawn here, you're not going counterclockwise. You're going clockwise. Everybody see what happened there? So heads up, please. Don't rely on this whole business about counterclockwise always being the right answer. It just isn't. It's the right answer. I guess you could say it's the right answer if you're going around the outside portion of the boundary, right? But as a definition, not acceptable. Okay. Pausing. Is everybody happy? All right. Okay, next idea. Now this is going to not be immediately clearly related to this business about boundaries that we just talked about, but it's going to turn out that it is. And again, this is part of the pieces that I have to develop in order to get to. I need certain tools and perspectives in place to be able to make the case for Green's theorem. So this is just the second thing that we need. This is actually an old concept. We've been doing this quite a bit throughout this course. I just haven't used this particular word, but it's the idea of what I like to call accumulation. And this is the whole is the sum of the parts. And like I say, it's an old idea. In some sense, every integral we've ever done in this class is an argument about an accumulating quantity. So for example, if I have this region right here, solid two-dimensional region, there we go, solid two-dimensional region. If I ask how much mass there is on this hole, and then if I ask how much mass is there on this part, and then how much mass is there on this part, well, the whole is the sum of the parts. The total mass is the sum of these two half pieces of mass. So that's all I mean by accumulation. The whole is the sum of the parts. And if you think about it, again, we've been doing this a lot. How do we approach problems that require an integral, aka a Riemann sum? Well, we argue that this, for step one, that the whole is the sum of the parts. It works for masses defined on two-dimensional regions. It works for populations that are distributed over regions. Anything else that you compute on a double integral of over a two-dimensional region has this feature, the whole is the sum of the parts. Okay. So just a little bit of lingo. Again, I call this the feature of accumulation. Said differently, the quantity in question, in this case mass, just as a lingo thing, I'll say mass accumulates over the region. That's just a streamlined version of saying mass has the feature that the whole is the sum of the parts. Said differently, mass is an accumulating quantity. Same thing, different lingo. Everybody okay? Now, naturally, the focus in this class has been to talk about accumulating quantities, because one of the big topics in this class is integrals, which apply when the whole is the sum of the parts. This has been the only thing we've needed to talk about. But I do want to point out, just so we're all clear on it, that there are some quantities that are not accumulating quantities. And I think an easy first example to talk about is perimeter. Perimeter is not an accumulating quantity in the sense it does not accumulate over areas. Now I want to walk through this carefully so you see exactly what I mean by this. In particular, what I mean here is that if you look at, let's see here, color choices. Let's do purple for the whole. Here's the whole. That's the whole area. Let's ask, what is the perimeter of this whole area? Well, the perimeter, I can draw the picture on here. Perimeter of this whole is that distance. Right, walking around the entire outside. So that's the perimeter of the whole. Okay, now let's look at the parts. Separately, let's look first at the left side here. Let's talk about what is the perimeter of just the left side. Well, the perimeter of just the left side is kind of all of this. There we go. It's that green distance. That's the perimeter of the left. Now we'll look at the right side. I think y'all can probably see this coming, but here's the right side. Where's the perimeter of the right side? About like that. And now we ask, is the purple distance equal to the green distance plus the blue distance? And I'm going to say, well, no, obviously not. Right, you can see right there in the picture, there's some green and blue stuff that isn't matched by any of the purple. So Here, in this case, looking at this quantity called perimeter, the whole is less than the sum of the parts. So this is not an accumulating quantity. And you can see the difference right here. Here is the difference between the whole and the sum of the parts. The difference is this edge gets counted twice as part of the sum of the parts. It's not there at all for the whole. Everybody on board? So, not everything is an accumulating quantity. Real quick, I want to emphasize, I'm thinking of accumulation over areas here, by which I mean it's the areas that I'm chopping up into pieces. That means that it's for a given area that we talk about the perimeter. So it's tempting to say that the perimeter is a feature of the boundary curve, because it's the length of the boundary curve. Importantly, we need to not take that point of view. Importantly, I want to think of perimeter as something that I associate to the area, because it is the area that I'm going to be chopping into pieces. I am not chopping the perimeter into pieces. I'm chopping the area into pieces. Does everybody see the distinction there? Everybody have any questions? Feel free. Okay. All right, so what's the difference? How come mass accumulates and perimeter doesn't? And there's different points of view you can take on this. I mean, in some sense it is what it is. But it is kind of tempting to say, well, look, there's a physical reason that mass accumulates, right? Mass is it's a concrete, visceral, it's stuff, it's actual, it's part of the universe that we live in. It's not some abstraction, that we made up. It's real. And just because I contemplate, I want to think of the mass on the left and the mass on the right as being different pieces, that doesn't make mass appear, it doesn't make mass disappear. So, in some sense, mass accumulates. It has this lovely property because it's physical. Right? Perimeter doesn't have this property because, perimeter is it's sort of a figment of our imagination. It's not physical. Right? It's not a thing. It's a kind of a mathematical construction, kind of a geometric construction. Right? And so the realities of the physical universe make no comment. They don't help us at all. And so they're free to be as non-accumulating as they want to be. Okay, very importantly though, this is not a perfect correspondence. There are some mathematical constructions that do accumulate. And this is a huge point. This is the nugget at the center of what we're developing here as Green's theorem, is the fact that we're going to have an algebraic/geometric, namely mathematical abstract construction that does accumulate. And here's what it is. It's boundary circulation. For any vector field, we need to be able to define integrals. So any continuous vector field, boundary circulation, which, by the way, is, I recognize this is, what do you call it, when you say something like family heirloom, the family is implicit in the prefix heir. What am I talking, there's a word for this. It's superfluous. Anyway, I don't technically need to say boundary circulation because by the definition, circulation is around a closed curve, which is a boundary. Anyway, I'm saying boundary here for emphasis. Boundary circulation is an accumulating quantity. Now, at a glance, it doesn't look like it. So I want to walk us through it, just like we did for the failure of perimeter. And I claim this is going to work. Here we go. Let's start with, let's see here. I'll do purple again. Fine. Let's look at the whole here. Looking at the whole region, what does boundary circulation look like on this whole region? Well, boundary circulation says I'm going to move around the boundary specifically in the direction that I'm supposed to. Because remember, the word boundary now implies that orientation. required. Right? So boundary circulation means I'm going to compute a line integral on that boundary curve. So there is a geometric, you might say, representation of boundary circulation on the hole. Again, the whole area. Again, very importantly, I don't want to think of this boundary circulation integral as being something we associate to the boundary itself. I want to think of it as something we associate to the area. You give me an area, I compute the boundary circulation. It's a property of the area. Okay, now let's do it for, let's see here, for the left piece. There's that left piece. What does boundary circulation look like here? Well, boundary circulation, again, following the rules about orientation. There you go. Just kind of this. There's the boundary of D1. Orientations respected. Boundary circulation for the region D1 would be computed on that green curve. And then likewise for the right side, D2, here's D2, boundary circulation is computed integrals along its boundary. That's this blue right here. And again, let's ask the question, is purple equal to blue plus green? And it kind of looks like it isn't. For kind of the same reasons that it didn't work for perimeter. Because I see that they match up, right? All along in here, the green and the purple kind of cancel. And then all along in here, the blue and the purple kind of cancel. And once you get rid of all the stuff that clearly cancels, there's leftover. And so what we have here on the screen, this green and blue pieces that are left over, this is the gap. This is the distinction. This is the failure. This is the difference between the whole and the sum of the parts. And here's the thing. It's zero. It doesn't look like it. You see a green and you see a blue and it's like, well, there's line integral there. That's surely you'll get some value for that line integral. But very importantly, notice that's along the same edge, but with exactly opposite orientations. And so on this same edge, opposite orientations, they cancel, and the difference between the whole and the sum of the parts is zero. Said differently, the whole is the sum of the parts, and boundary circulation accumulates. How are we doing? Everybody with me? Okay, so again, this is deep down, fundamentally, this is what makes Green's theorem work. And taking it back another step, this is why it's important to have just the right convention for what we mean by the word boundary. It is specifically because we made a very specific choice of convention of what we mean by boundary that we guarantee that we in fact did have opposite directions along these pieces. Right? So, boom. Okay, pausing though. I want to make sure everybody's okay. Does anybody have any questions? Okay. All right. Now, I added this line in the process of sort of dividing D1 from D2, and that's where we had the two pieces that canceled. I want to point out you can divide it as many times as you want. Go crazy. Chop up your domain, in other words, into as many pieces as you want, such as I have in this picture here, and the exact same thing happens. So, for example, if I look at this piece of the domain, I've chopped up my domain into a bazillion little pieces there, right? Not even drawing the whole domain, just looking at just this part down here. On that piece right there, the boundary, line integral along the boundary, namely the boundary circulation, consists of those 5 little line integrals. And then I can look on this piece here, do the same thing, and I get boom, 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 boom. And then I can do the same over for this piece, which gives me these, etc., etc. And notice we get just multiple instances of morally the exact same kind of cancellation. So looking at this edge right there, highlighted in red, this edge is going to appear twice in the summation of all these line integrals with exact opposite orientations, cancel. This edge here, twice, opposite orientations, cancel. This edge, twice, opposite orientations, cancel. Etc. Boom, boom. All of these pieces here, these all cancel because these edges, each one that I'm highlighting in red here, appears twice with opposite orientations, and they all cancel. What's left over? What are the ones that don't cancel? Let me clean up my massive mess that I've made here. The ones that don't cancel are the ones where there is nothing on the other side to cancel with. Right? And so, for example, this little piece down there and this little piece right here, these pieces of curve, they don't appear twice because there is nothing on the other side. So there's nothing to cancel with, and they just remain. And you'll notice that the pieces that don't cancel are exactly the pieces that are part of the boundary of the whole. So chop it up all you want. The whole is the sum of the parts. Everybody all right? Okay. All right. All right. So now I've already said this, but I want to say it again. I think this is a really important point of view. When we're doing this, when we're talking about boundary circulation, we're thinking of it as having this feature of accumulation. We have to think of it as accumulating over the area. It is the areas that I'm chopping into pieces and over which I'm doing summations. So I want to think of boundary circulation as a feature of the area. Please don't think of boundary circulation as a feature of the perimeter. Now, the reason this is confusing is because when you look at boundary circulation, and again, let's look at the whole here, the whole region. Where do we actually compute the boundary circulation? Oh, on the perimeter. Right? That's where it's computed. But importantly, we're not taking the perimeter and chopping up the perimeter into little pieces. That's just not what we're doing. That's not what that's not the argument that we're making. We're making arguments about chopping up the area. So we need to think of boundary circulation as a feature of the area, not as a feature of the perimeter. So along those same lines, I encourage you to think of it as happening on the area. Even though it actually is computed on the perimeter, think of it as happening in the area. And so let me give you an example here. So let's look at this piece, and I've chopped this up into a bunch of little pieces, and I could reasonably ask, there's a boundary circulation. I'm going to phrase this the wrong way first, so you can see how confusing and nonsensical it seems, and then I'm going to phrase it the right way so you can get more satisfaction. Question: how much of this boundary circulation is happening here? And the question seems ridiculous. Well, none. The green circulation's computed on the green curve. The purple circulation's computed on the purple curve. They're not the same curve. They don't overlap at all. There's no seeming connection between the green and the purple. It seems like a ridiculous question, right? And I claim that the reason this seems ridiculous is because we're not thinking of circulations the right way. Again, you should not think of circulations, even though they are computed on the perimeter, should not think of them as being something evaluated, something that we associate to the perimeter. You should think of it as something associated to the region. Let me say it again now. Same question. If I were to look at the boundary circulation for this whole green region, And if I were to ask how much of that boundary circulation of the whole region happens in this purple region? Oh, okay, sure. Well, there's a tremendous overlap, right? This purple region is part of the green region. And any accumulating quantity that I have, let's take mass, for example. If I ask how much of the mass in the green region is in the purple region, no problem, right? Perfectly reasonable question. How much of the population in the green region is in the purple region? Perfectly natural question, no sweat, nothing weird about it. And so likewise, I want to do this for all accumulating quantities, all quantities that accumulate over the areas, that accumulate when you chop up the areas. I want to think of them in this same way. And so, how much of the green circulation happens on the purple? Well, the green circulation says right here, the green circulation is 33. I made this number up. This is there's some vector field, whatever. I don't want to get lost in a bunch of algebra. But let's suppose that this green circulation is 33. And you notice that all these numbers in the interior, when you add them up, they add up to 33. How much of that green circulation then happens in the purple? Well, it says right here, 6. Very straightforward. Right? If you think of boundary circulation, despite where it's computed, if you think about it as associated to the area, as if it's distributed across the area, I know it isn't, but if you pretend that it is, right, then everything makes sense. And, so let's ask the question, but should we think of boundary circulation as happening on the areas? And my response to that is, it behaves like it is, so you can, and therefore, in order to have intuition for the way it behaves, you really should, because it behaves that way. Okay, so that's the punchline of all of this. You want to think of boundary circulation like we think of all other accumulating quantities. You want to think of it as a stuff. You want to think of it as kind of like mass in a way, in that it is a stuff that's distributed over the area. Is that okay? Is everybody on board with this this point of view? All right. Okay, so we're almost to being able to state the theorem in question. We've got most of the ideas developed. A few more things we have to say. I just want to remind you all of another thing. When you have an accumulating quantity, such as mass, right, you can talk about mass per unit area, aka mass density. Old idea. We've been doing this for a long time. Y'all have been doing this since long before you got to this course. Right? Mass, you can talk about the mass of a whole, but you can also talk about a small little piece. You can talk about how much mass is in that piece, and therefore you can ask how much mass is there divided by how much area is it distributed over. So mass per unit area, aka mass density, perfectly natural, reasonable idea. So now the eyebrow raising but ultimately reasonable analogous idea is to say, well, you know what? It's the same with boundary circulation. Boundary circulation also I can think of as associated to an area. It's an accumulating quantity over areas. I can talk, therefore, about the amount of boundary circulation there is for a given area. I can divide that by that amount of area that it's distributed over. And again, I have accumulating quantity per unit area. And this too, we're going to call a density. This, because the accumulating quantity is circulation, we're going to call this circulation density. And that's a weird concept, right? I warned you in advance. This is going to get weird. Here it is. It's very weird. The thing that makes this make sense, though, you have to think, as I was urging on the previous page, you have to think of boundary circulation, even though it looks like it's on the perimeter, you should think of it as being distributed over the interior. It behaves algebraically as if it's distributed over the interior, so you should think about it as if it's distributed over the interior. And as such, stuff per unit size, perfectly reasonable. This is the next sort of really huge idea in developing Green's theorem. This idea of circulation density. Now, there's some notation that I have to kind of get said. Circulation density, this formula. We can compute it. It's a calculation. There's steps and details, and it's perfectly doable. It's in the book. You can look and see that calculation in the book if you want. To my mind, that's details. I don't want to focus on details that are just a mere calculation. So I'm just going to tell you what the answer is, and that is for a given vector field P comma Q, circulation density is this formula right there, dq dx minus dp dy. If you want to take a look at the argument in the book, that's fine. Go ahead. It's very straightforward. Some details. But it works out very nicely. This is the answer. Feel free to just trust me on this. Totally fine. We are building towards what's going to be our final punchline right here. We're building towards something called Green's theorem. And as such, this operator, I think it makes sense to call it Green's operator. And I think anyone to whom you say Green's operator would know what you're talking about. So I call it Green's operator all the time. I think this is very natural to call it that. With that in mind, I also write it as GRN of F. And I really have to confess, I don't remember where I got that from. It's possible I may have made this up myself. I'm not sure. I think also I might have copied it off of someone 30 years ago, and I just don't remember. But either way, I think this makes sense. GRN is suggestive of Green's operator, which is what this fundamentally really is. This is the big point of Green's theorem. So why not call it this GRN of F? Now, an alternative that I think is great, I like this quite well, ROT. Why would we call this ROT? This ROT is, I know it looks like rot. Right? It's an abbreviation of rotation. Why would we call this rotation? Well, don't forget what circulation is. Circulation, after all, is representing the extent to which a vector field is flowing along a curve, the curve going around in sort of kind of circular, like if you were to keep track of the direction that it's going, it makes a full loop, like a circle does. So, in some sense, circulation is a measure of how much the fluid is rotating. And I made a case last time that if you were to take a fall leaf, let it drop into a creek or a river, and watch how that leaf moves, that leaf is not just going to maintain its arrangement. It's going to turn. This is easily observed. You go out to some creek somewhere and drop a leaf in there, and you'll find that it rotates, literally rotates as it goes downstream. So, rot makes great sense. Love it. And now to the ones that I don't really like. I guess I'm going to put these in red. Some people call this curl. Y'all may remember back in chapter 3 we talked about curl. But curl is a vector. This is a scalar. So it seems pretty different. Now, this thing, Green's operator, and the curl that we talked about in chapter 3 do play very similar roles. There is a theorem coming up in chapter 7. It's a lot like Green's theorem. And curl is going to play the analogous role there. There's very strong analogies, but they're sufficiently different that I think it's weird to use the same term curl to refer to the two, I think, significantly different things. So I'm not really a fan. I mention this only because, again, you're going to see this. So, this is out there. Plenty of people will call this curl, and okay, so fine. And if you want to make sure you understand what they mean when you do see this, I encourage you not to call it curl yourself. But anyway, and then one I really don't like. This one's just kind of wrong. This, and let me uncircle. My picture's getting messy here. This del cross F, that doesn't even make any sense. F only has 2 coordinates. You can't do a cross product if one of the things only has 2 coordinates. It just doesn't work at all in my way of thinking. Now, again, there's a connection, and anyway, let's not get distracted by why this is something I don't care for. But I do think it's very sketchy notation. I encourage you not to use it. And we're basically ready to, we've basically already proved Green's theorem here. I guess we don't have quite time. We're already out of time. I got to stop it here. But all the components that we need in order to state Green's theorem, we already have. Next time, we're just going to put the pieces together and start doing examples and applications. Y'all have a good rest of your Wednesday. See you later.